All right. Welcome, everybody. And today we're going to talk about Lecture 5. Actually, on Canvas is the Lecture 6 modules in your Canvas. But Lecture 5 is the slides we are going to go over with. Okay. That's what it is. Okay. Lecture 5, this lecture, we start talking about simplex tableaus, and from the original simplex tableau, and we're going to transition into revised simplex method. And the course material is coming out of your handwritten handout from page 36 to 41, or you can directly follow the slides printout we have online. Let's review the simplex tableau we had in the original simplex method. We have a column 1, which is the z, which is our objective function value. And then we have a section of so-called basic matrix. And in the basic matrix, and the first row is always 0. And then the corresponding tableau should be identity columns. Then we have a so-called non-basic variable on this section, and we can calculate their shadow price called zj minus cj for each one of them. It's actually equal to cb transpose times b inverse times m minus cm. And CB transpose, later on we're going to tell you that's omega, which is our do variable. Also, this is the right hand side column. Okay, this is the right hand side column, and then the first row will be the current objective function value, and the rest of a row will be the current basic solution. Most importantly, then in the middle is the for corresponding to the non-basic variable, they are the current tableau's value. We call it y. Y equals to basically b inverse times n. So we do some sensitivity analysis. Look at the objective function value here. Okay, objective function value here, right here, and then z hat equals to cb transpose times b inverse times b minus b inverse times n times xn, and plus cn transpose times xn. So here we're going to collect terms for xn together. So first part we have is cb transpose times b inverse times b. And the second part, we have CB transpose times B inverse times N minus Cn times Xn. Okay. And the CB transpose times B inverse, again, we define them as a separate variable called omega. The omega equals the CB transpose times B inverse, and also the Zn. Zn is previously defined by omega times n, capital N. N is the non-basic columns matrix, non-basic matrix. So we can rewrite the things a little bit shorter term called omega transpose. Omega transpose times B and Zn minus Cn times Xn. So this is pretty much and simplified versions. This is a long equation. We're using some variable substitution in that case, and we do have more. And later on, we're going to see that the omega, we're going to define them as a do variable in the future, do solution. So the first part is the objective function is omega times b. And the second part is the corresponding to non-basic solution variable. Is actually equals to cj minus zj times xj. Xj are the non-basic variable. Let's take a look how this would work. So first we're going to try to see the partial z hat over partial b. If you look at the person, taking partial along the bj. So we see that actually in this case is actually omega. All right, and also we can see that the partial z over partial xj for xj are non-basic. So that's the second terms in this equation. So taking partial z hat over xj right here, xj right here is basically cj minus zj. So if I take first derivative as corresponding to xj, and result will be cj minus zj. So this is what this two are. Okay, so fairly simple. And let's look at the first equation, partial differential equation, and it's a partial z, partial bi. And each one of the bi start with a certain z if it keep increasing bi, and then we eventually can decrease our objective function even more. What is bi? Bi is the right-hand side for your constraint, meaning for that particular resources or constraint, we relax them. Of course, we could get a better objective function value in z hat. So, in addition, let's look at the other ones. Okay, x sub b is our basic solution right now. The solution for the basic variable represents the b inverse times b minus b inverse times xn times n times xn. Also, for a particular xj, which is a non-basic variable xj, we can rewrite the things as a little bit simpler. If all the other non-basic variables stay zero, only xj is going to change from 0 to a positive number. Then we will have the same thing. B inverse times B and sigma all the B inverse times AJ times XJ. What is the AJ? AJ is the original column corresponding to XJ. Okay? And also we know B inverse times AJ equals to YJ. And B inverse times B, we can convert it into the current basic solution, current solution for the basic variable. So fairly simple, and we can write it in this manner. Okay. So I want you to start understanding, if I take this value, partial derivative of xb corresponding to xj, it should be negative yj as our solution. Okay, negative yj. And that also means when a non-basic variable xj increase from 0 to a positive number, and then xb, with one of the basic variable, will decrease by yij. So this is what it means originally based on the derivative. If xn equals to 0, then I can directly, so that means this part is 0. Okay, this part is 0. Then the xb should be equals to b inverse times b directly. Take a look at the multiplication b inverse times b. It should be all the b columns, b inverse column times right hand side b1s to bm. Right hand side b1s to bm. And these are the columns for b inverse matrix. And therefore, xb equals to b inverse times b. If I take the first derivative of b xb, which is the basic variable according to the right hand side, bj, is basically what the ij's elements in the B inverse matrix multiplied by -1. So this is a pretty straightforward answer. So this particular slide showing two results. First result is the current basic solution. If xj is moving from 0 to a positive number, then each unit of xj increase, actually, b is decreased by yj amount. Okay, what is yj? And yj equals to b inverse times aj. And aj is the original column for your constraint matrix corresponding to xj. So this is the first result we get. Second result we get is if we change the right hand side resources, the xb I, which is the i's elements in B matrix, is changing by partial over partial bj, okay, which is the right hand side. If I relax the constraint, increase certain constraint, and the changes will be actually negative bij inverse. So it's the bij elements of the inverse matrix in our case, right here. So these are the two main results we're getting on this slide. And let's review the last slide we have. Okay, yeah. If I change the right-hand side of the i's constraint, the amount of the objective function I can improve is based on omega j. Where is omega j? Omega I, once more, equals to CB transpose times B inverse for the i's element, that one. If I change also the non-basic variables, one of them, if I change them from 0 to 1, and every unit of that change will be Cj minus Cj. So that's fairly straightforward result. We want to make sure you guys know. Okay. Next slide, we're trying to see if we can find the initial basic feasible solution real quick. It is possible to transform a linear programming problem into a standard form. The standard form is, first, we have a minimization problem, and second, we have an equality constraint and non-negativity constraint. Okay? If B, right-hand side B is greater than 0, assuming for all this situation, if not, we can multiply the entire equation by -1 to make it. So, if A matrix contains identity matrix, then the initial basic feasible solution is easy to find. We're just assigning those columns as a basic column, so the initial basis will be identity. And also, since the basic matrix B is identity, then this B inverse is easy to calculate as well as identity itself. Then B inverse times B, the first initial basic feasible solution will be I identity matrix times B will be actually B itself. So that's fairly easy. Let's look at the example. Minimize x1 minus 2x2 and subject to x1 plus 3x2 less than equal to 8, negative x1 plus x2 less than equal to 3, x1, both x1 and x2 are non-negative. Since they are both less than or equal to constraint, we're able to adding two slack variable x3 and x4 into my system and make it equality constraint. So we basically transform into a standard form of linear program. Now we have a 4, that's 4 variable instead of a 2. Let's look at another example. What if we have not all of the constraints are less than equal constraint? So what we have is we can actually, this example, we have x1 plus x3, 3x2 greater than equals to a as part of our constraint. So to convert this to be equality constraint, we adding a surplus variable x3, and this is surplus variable x3, and then we adding a artificial variable variable a1. So this will still make it an equality constraint. The reason we're adding this artificial variable is we have an identity matrix right here. Initially, we're going to pick the x4 and a1 are as basic variable, and rest of the variable as non-basic variables, and set their values to 0. So this equation is easy to solve. A1 equals to 8, x4 equals to 3. That's my initial basic feasible solution for sure. Okay? And in a later iteration, we're trying to get rid of the artificial variable in our basis, and that's the target. Let's look at the other one. This one we don't have a greater than equals to constraint. However, we have a equality constraint. Negative x1 plus x2 is equal to 3. Okay, so in this case, we're just simply adding a artificial variable x82. So therefore, we have initial basis right here. Okay, initial basis right here. So this is also possible, and these are the 3 different ways we're adding either slack variable, either surplus variable, and artificial variable. For equality constraint, we're directly adding an artificial variable so that we can easily start with the initial basic feasible solution. Okay? The last 2 cases, A does not contain a identity matrix to begin with, and that's why we're adding an artificial variable so that we can start with the identity basis in the beginning. Now, we're switching gear. We're going to start talking about revised simplex method and how the computer actually implement the simplex method, which basically that's our goal. It is the way actually simplex method is implemented in the computer and especially in the commercial software and solving linear program. This method has 2 major advantages. First is take much less memory storage to run your program, so the program can run larger models and in practice. Second, and the method is avoiding any cumulative runoff errors in the calculation when you pivot your numbers from Tableau to another Tableau, and this creates a lot of accumulated runoff error. In hand calculation, we're using fraction calculation so we don't lose the precision. However, the digital computer always come in with a floating point number. If you run this for many iterations, the runoff error could cost you a lot. So first, let's review the so-called original simplex Tableau, how it looks. And actually, this, and we have from x1 to xn. Okay, so there will be n column. n columns. And this is one column only. All right, so we have n plus 1 columns, and how many rows? This is one row, and down here I have m row. So this particular matrix in the original Simplex Tableau, I have n plus 1 column and n plus 1 rows. And this is every single calculation we have to make for each one of the iteration. So first, once we figure out the B inverse, I need to calculate Zj minus Cj for each column right here. We need to calculate Zj minus Cj for each column and the right hand side. Also, we need to recompute for each one of the column what is their yj. So remember, B inverse times aj equals to yj, and then recalculate the current basic solution. So this is quite a bit of a computational effort to maintain this Tableau. Of course, in a small problem, we'll do it by hand. This is not too much trouble. But if you're dealing with a problem with a couple millions variable and a couple hundred thousands of a constraint, and then this is going to be a major problem. Again, we reviewed what is the original Simplex Tableau is, and remember what we have previously, Zj minus Cj equals to CB transpose times inverse times AJ. CB transpose we can pre-calculate since they are the same for each one of the column. Okay, and also, and then we can first define omega equal to CB transpose times inverse. Then we using omega instead because omega is pre-calculated. And in fact, omega is the due solution in our Simplex Tableau. But in the revised Simplex vessel, we can simplify this. See all this, the original Simplex Tableau, what we have. Only thing we need to update each iteration is the B inverse and the omega. And omega equals to CB transpose times B inverse. So once we determine B inverse right here, and we can quickly recalculate the omega. Once we calculate the omega, and we can update the first row and each one of the solution accordingly. So something we would do is each iteration, we only calculate. So here we still have n plus 1 row, but only recalculate each iteration m plus 2 columns. So since m is fairly small compared to n, so we save a lot of storage space. So only keep the necessary information and recalculate each iteration. One of the things is, okay, and that's the pivot column, and only one column only. And that's the right-hand side column. That's also the single column. And then this is B inverse and omega. And B inverse we recalculate every iteration, and the omega is recalculated based on CB transpose times B inverse. Okay, CB transpose times inverse is omega can be recalculated once we had B inverse. And the CB itself is the original data from the problem, so we don't need to recalculate anything. Giving you example how this saving is going on. So this example, we have the C is the cost coefficient, the C is the cost coefficient, and then A is the constraint matrix. So we have total 9 variables, okay, x1, 2, 3, 4, 5, using the last 3, x7, 8, and 9 are the basic variable. right hand side is a 644 is the right hand side. So if we choose the last three columns as the basic, initial basic basis to start with, so they're equals to identity matrix, therefore the B inverse is inverse matrix is also identity matrix. And omega actually equals to C transpose times B inverse, which is 0, because all C7, C8, and C9, the cost coefficient corresponding to X7, X8, and X9 are 0. So therefore, their current omega equals 0 as well. Next, we can use it once we have omega and B inverse, we can calculate Zj minus Cj, which is the first row and the previous slide, equals to omega transpose times Aj times minus Cj. Since omega equals to 0, actually this Zj column is actually negative Cj, because omega all equals to 0 to begin with. And the maximum of those will be 4 to begin with, which is this guy, x5, corresponding to x5. So we can recalculate the new column corresponding to x5 by using B inverse times A5. A5 is the original column for x5, which is 102. And the B inverse right now is identity matrix, so it's still 102. Okay, next slide I'm going to show, here we're going to show you efficient way to storage the information. And I have a color differently, okay? And left, the first column will represent who are the basic variable, x7, x8, and x9. And the middle, and that's my B inverse, where it's storage. On the top, which means the Zj minus Cj, we have on the top, corresponding to each one of the basic column. And also, on the right hand side, that's the right hand side, equals to current basic solution, B inverse times B. And this corner will be my current objective function. All right? Next step, the same table we had before, B inverse, Zj minus Cj, the right hand side on the upper right corner, that's the current objective function, which is 0. Then since we adding x5 as an entering variable, and we need to do a minima ratio test to decide who is the leaving variable. So that's the original column, Wi-Fi column for x5, and here I have is equal to 4, and then taking each one of the y divided by 6, so 6 divided by 1 will be 6. And this is second element is 0, so didn't care. And the last element is 4 divided by 2 equals to 2. So between 2 and 6, 2 is the smallest. So therefore I decided x9 is the leaving variable. And then I'm trying to say is, since x9 is the leaving variable, I want to create this column identical to x9 column, okay, right here. So 0, 0, 1 down here and 0 on the top. So I would need to do is divide this whole column by 2 to make this element 1. Then take this column times -1 added to this row, and this row divided by 2 times -4 added to this row. So therefore, that's the result. So yes, we do actually do some pivoting in a sense. However, the stuff we're pivoting is a limited amount of the table, only small portion of the table, including your current basic B inverse matrix, just with one more column, which is the entering column, and then you can reach the new Tableau. And what does this Tableau means? The center part, the yellow part, still the B inverse. That will be the new B inverse. And the upper part, and this part, will be your omega, and which is equal to CB transpose times B inverse. All right? And now this is your objective function value negative A, has been improved. So here we can actually show you, if you look at this, B equals to now A7, A8, and A5 right now. And X5 entering the basis, and the corresponding B inverse will be exactly like the yellow area over here. Okay, these two are exactly the same. And also we can recalculate the omega transpose is basically 0, 0, negative 2 is exactly equal to here. So I really don't, I use this small Tableau, I really don't need to do these two matrix multiplication. I just need to do one iteration, area of pivoting, and then we will have already calculate my omega and B inverse. So B inverse can be getting from here, and omega is the top row. Everybody okay? If that's okay, then we can use this to recalculate all the Zj minus Cj for the non-basic column. And non-basic column equals to, basically, omega Aj times omega transpose times Aj. Aj is the original column, which given by the problem. Cj is also the original cost coefficient given by the problem. So other than omega, we need to recalculate every iteration. The other ones are just input data. Okay? For this iteration, we figured out x2 is the largest. Okay? Largest is Zj minus Cj. So therefore, x2 entering the basis, and recalculate the y2. This is probably the only calculation, matrix calculation you need. Simply B inverse times A2. A2 is the original column 2 corresponding to x2. And then we'll see the next slide. Okay? This is the Tableau I copied from the previous slide. This is the, in the middle is the B inverse. On the top is the current omega. This is the objective function. This is the current basic solution. And then we adding this y2 column, okay? And we therefore we do the minima ratio test. Since these two, this one is negative, that one is 0, so I don't need to calculate. I only need to focus on the positive elements. It's based on the minima ratio test rule. And then we know the x7 is the leaving variable. Therefore, we can redo that. x7 is leaving variable, x2 entering. So I'm going to do the pivot, which is elementary row operation, to make this row, y2, looks exactly like the first row right here. So after that, we do the pivoting, and this is my new B inverse. Okay, B inverse in the middle. And this is my new omega. This is my new objective function. This is new basic solution. And therefore, based on this, I can also recalculate. B inverse is already here. Omega is right here. So the yellow part you don't really need to calculate like that. You're through a one iteration of pivot, you should get that already in your Tableau. Then using omega and B inverse, we can calculate all the Zj minus Cj based on omega times Aj minus Cj. Therefore, this iteration you figure out all the non-basic column, their corresponding Zj minus Cj are negative. Okay, in that case, is proving there's no way I can improve my objective function anymore, and the current solution on hand is optimal solution. So this is a small example illustrate how the revised simplex method can save the storage, and also it's much more efficient to do the pivot, it's much more efficient to do the calculation and in any sense. But once you have the B inverse at each iteration and the omega, and you can calculate based on B inverse, and then you can basically revert to the entire Tableau anywhere you want it. So this will conclude this lecture for now, and we will go to lecture 6 next time, and we will have more exercise on this topic. And okay, I'm going to conclude the recording.